Welcome you all to this course on electron diffraction and imaging. So far we have covered conventional transmission electron microscopy, In this we have looked at different diffraction techniques, as well as different imaging techniques. The diffraction techniques are essentially parallel beam diffraction, CBED, convergent beam diffraction, and Kikuchi diffraction, which is nothing but a divergent beam diffraction. Similarly, in the different imaging techniques, we have covered bright field imaging, dark field imaging, then weak beam imaging. Then the other techniques which we have covered are high resolution transmission electron microscopy. Similarly, stereographic projection, which is required for analyzing as well as interpreting relationship between different planes and directions in crystals. Okay. All these aspects have been covered. Today what I thought is I will talk about some recent trends and new advances in electron microscopy which you should be aware of. What are the techniques which are available? One of the technique which is available in an electron microscopy is called as an electron tomography. What is tomography? Tomography is nothing but getting a 3-dimensional image of a sample, which you know that CAT scan, which you call it computer aided tomography. This is quite similar to that, because normally what happens in an electron microscope is that though the beam passes through the sample and through the full thickness, okay, the image which forms on the screen essentially a 2-dimensional projection of the 3-dimensional information which is available. Looking at that image taken in one direction, we will not be able to make out what is the shape of this particle. Okay. This information we can get it using electron tomography. This has lot of applications in macromolecular biology, then in finding out the shape and size of second phase particles, all these aspects which we will cover. The next one is which I wanted to talk about is Lorentz microscopy. What is Lorentz microscopy? This is a technique which is used to look at magnetic materials, especially to find out how the magnetic domains are distributed, these information which we can get it. Okay. This we will cover. Then the other one is scanning transmission electron microscopy. This technique I had already covered, and I had told you also that using the scanning transmission electron microscopy we can that is using the beam as fine as possible, especially using CSR, aberration corrected probes. One can get beam sizes of the order of 0.1 nanometer with good beam current using an FEGS, the field emission Ganasdott filament, and using this we can scan on that sample surface, and the electrons, the transmitted as well as the scattered electrons, we can collect it. Okay, depending upon the interaction which takes place, there will be a variation, and this can be used since the beam size is very small. We can almost get an atomic resolution, and interpretation of these images are very easy also, relatively easy compared to the image which we get it, interpretation of images in high resolution transmission electron microscopy. Okay. These aspects I will not go into detail, which I have already discussed at sufficient. Using this same facility, okay, in a scanning transmission electron microscope, using annular apertures, that is apertures which collect information, okay, at angles which are greater than maybe 3 degrees. Okay. One can get electrons which are essentially not a Bragg scattering, it is essentially Rutherford scattering. So, these are all incoherent scattering, and the intensity of the scattered radiation is proportional to Z, the Z squared, the atomic number, that is intensity I is proportional to Z squared. Okay. And here again, since we use a beam which is very fine, okay, we can get atomic resolution information about the position of atoms in that sample. This aspect also has been already covered. Another is CS corrected high resolution, that is aberration corrected transmission electron microscope, which also has been covered. I talked about what is the advantages of using this microscope, how this gets information about the atomic, how this microscope could be used to get information about the atomic structure of the samples, not only the ideals, not only ideal structure, but also the defect structure. Another technique which is very important, which is finding prominence, is electron holography. This is a technique with which we can get information about not only the phase, not only that from the image which we get, we can get information about the phase as well as that amplitude, so that generating atomic structures from this information is relatively straightforward. This we will talk about it. Okay. The another type of microscopy which I will talk about is time resolved microscopy or dynamic electron microscopy, or we can call it as a pulsed electron microscopy. Okay. This also has got a lot of applications which we will talk about. Orientation microscopy is one, like in SEM you know about EBSD is used to get information about how different grains are oriented. Okay. Similar information could be obtained in a transmission electron microscope also, and these aspects I have already covered. Okay. First we will talk about electron tomography. What is electron tomography? Okay. As I mentioned, it is we can get 3-dimensional information about a sample. How exactly it is implemented in an electron microscope? As I mentioned earlier, in an electron microscope we get a 2-dimensional projection of the 3-dimensional information. So, we do not get correct information about the size of the objects. For example, suppose we have a ellipsoidal precipitate is there. So, if you look at this cross section in this direction, it looks like an ellipse. Okay. If I look at this precipitate from this direction, this will essentially look like a circle. Okay. Depending upon which direction I look at that sample, I get different information. In between directions, if I look at it, this will be essentially, the size will be looking like this. Okay. So, if you take one picture and we get a size, if it is like a circle or if it is like an ellipse, we may not be able to talk anything about what is actually is the shape of that sample. This information is really necessary when we wanted to find out the interaction of precipitates with dislocations, the separation between the particles, all this information, three-dimensional information about the size distribution, size, shape as well as the distribution is very much necessary. To get this information, what is done in an electron microscope is essentially we have a sample. The sample is put on a holder. Nowadays they call it as a tomographic holder, special holders are available. Or essentially what it is, you keep a sample like this, make the beam pass through that sample, okay. Then tilt the sample gradually over different orientation, okay, like in both these directions, okay, making sure that the beam falls exactly at that same area, and collect all the images which are formed for different tilts, okay. What is essentially is going to happen is that depending upon if a precipitate is here, depending upon the tilting of that sample, the precipitate also will change its orientation with respect to an incident beam, so that the shape of the particle which we are getting it, as well as the contrast also will vary, okay. Both this information which we have to use, that is using image processing technique, we can stitch all these images together and construct a three-dimensional image of that sample. This is a lot of computational work, it is essentially an image processing, okay. Using this we can get information about how this particle looks like, so that otherwise looking at one image we will be getting an information about the particles whose morphology is not correct, okay. So, this sort of work can be done in both in bright field as well as in dark field. Doing it on an optical scale with a light scattering, it is easy, whereas in an electron microscope we know that especially we are dealing with diffraction contrast, depending upon the different orientations, and if we tilt slightly the contrast varies considerably. So, one has to take a lot of care to see to it that the same diffraction spot is used, okay, irrespective of what the tilt which you have used to collect that image, okay. Where exactly this becomes necessary is that when we deal with lot of big macromolecules, when we are looking at it, what is the shape of these molecules, okay, that if you wanted to find out, there this electron tomography helps a lot, okay. This is one technique which is becoming extremely popular, and it is being used also, okay. The other technique which is being used very frequently is Lorentz microscopy, okay. What is Lorentz microscopy, okay? The term comes from that Lorentz force, okay, that is if a magnetic field is applied, we know that magnetic materials, they feel a force, okay. That force is called as the Lorentz force, okay, that is why it is called. We know that when we with a conventional electron microscope, when we wanted to look at a sample, okay, the lenses which we use, especially the objective lens, okay, all the lenses are electromagnetic lenses. Because the lenses are electromagnetic lenses, if the sample is conducting but it is non-magnetic, okay, then the magnetic field does not affect any of the contrast from the sample, because that magnetic field is essentially used to make the beam pass through that the beam which is passing through that sample, okay, which gets scattered in different directions, okay, they are being focused to a point, and this acts like a simple lens, what is essentially is going to happen when the sample itself is magnetic is that as the electron beam enters into the sample, the magnetic field can vary locally at different points in the sample. Suppose different domains are there, magnetic domains are there. Depending upon the domains, the electron can interact with the magnetic field, and Lorentz force will act on it, and it will just shift the beam in different directions. This sort of shift, what is going to happen is that the beam which has already been aligned, okay, now the whole alignment has, goes awry. This is one of the problem with magnetic materials. So, looking at the magnetic materials and getting microstructure information about it is extremely difficult, but it can still be done if we use very small mass of the magnetic material, okay, and some precautions have to be taken that the sample is sandwiched between two grids or it is glued to a grid so that it does not fly off, otherwise it creates a lot of problem in the microscope. Okay. But the same magnetic behavior of the sample itself could be used to get information about the distribution of domains in that sample. This microscopy is called as the Lorentz microscopy. Okay. In this, what is being done is that normally the objective lens which we use, they give a quite high magnification, about 50 times, okay, and most of the time if the sample is immersed within that, for the lens which we use, if you look at the focal length, it is about 2 to 3 millimeter, and then the sample is almost kept within that, it is, we call this, it is immersed within that field itself. Okay. So, the strong magnetic field it sees it. So, if we wanted to use the Lorentz that is the magnetic property and to get information about the distribution of the magnetic domains, one thing which one can do is essentially use a low magnification and use a lens whose strength is very small, or in a microscope what is done is that in sometimes the objective lens itself can be switched off, and the intermediate lens which is far away, that can be used to form the image, a low magnification image. By using that, okay, the effect of the local magnetic field, how that is how this objective lens magnetic field, okay, is going to affect that optical alignment, that can be reduced considerably. Okay. But apart from that, what is it which is going to happen with respect to a sample? As the electron beam enters into the sample, okay, depending upon the direction of the magnetic field, okay, the electron will be just scattered in slightly different directions, that is the path of the electron will be changed. Because of this, suppose we try to get a diffraction pattern from that sample. Normally in a non-magnetic material, we will be getting one spot, because that electron path is affected by the Lorentz force generated by this magnetic field. Depending upon which directions the fields are there, the single diffraction spot will split into multiple spots. Okay. That is what essentially is being shown. In this case, there is 1, 2, 3, 4 spots are there. Okay. And if we put apertures around all these spots together and try to form an image, then only the magnetic domain boundary becomes bright and the other regions are. So, this way we can identify where the domain boundary is. Okay. Or we can put an objective aperture and try to choose only each of these spots and try to generate images. When we do, these images essentially give the distribution of the magnetic domains. This is in the case of a nickel 3. So, these images are called as Foucault images. Okay. Generally, the direction of magnetization is normal to the direction of the spot splitting in the diffraction pattern. what all the uses, this can be used to find out the size. Looking at this sort of micrographs, we can find out the domain size information, we can get it. But from these images we can't get any information about the magnetic field itself, that is magnetic induction. That information cannot be obtained. No quantitative estimation can be done from Lorentz microscopy. Okay. That is what we talked about is in a conventional transmission electron microscope. Okay. In a scanning transmission electron microscope also, we can make the beam scan on that sample surface depending upon the magnetic direction of the magnetic field in different domains. The electron path will be changed accordingly. Okay. So, they will be coming in different directions, okay, when they come out of that sample surface. Okay. The detector which is used below in an STEM, either we can use a single detector to collect, or we can split the detector into few quadrants. Okay. Each quadrant can collect that electrons which has been scattered in different directions. Okay. If this information which we collected, okay, we can use each one of them to form an image. We know the electrons which are scattered in each direction. From that we can get how the magnetic domains are distributed. We can add, subtract information from one quadrant to the other, so that we can manipulate the image contrast and get information about the distribution of the magnetic domains. Okay. This is an example which is for magnetic domains in iron. Okay. These sort of images are called as Foucault images. Okay. There is another way in which we can get information about magnetic domains. This is using Fresnel image. These are called as Fresnel images. What is essentially done is that we know that if we change the focus a little bit, okay, around a sample which contains a hole, okay, we know that around the hole closer to it we get some fringe pattern, okay, alternate bright and dark fringe patterns which are getting it. Okay. This fringe pattern comes from Fresnel diffraction which is taking place, because from one side to another side there is a potential variation is there. Okay. This information itself could be used, and we know that in a conventional microscope, when it is in perfect focus, okay, the contrast of the image is the minimum. Okay. This is an example of a sample where you can see that when it is in a perfect focus we do not see any image, but when the sample is magnetic, especially magnetic domains are there, from one side to other side if we go, the magnetic potential, there is going to be a sudden change is going to be there, because of which if we defocus a little bit we will be getting a bright and dark contrast. Okay. This contrast itself could be used to identify the magnetic domains. That is exactly what is being done in this particular case. Okay. In fact, the same Fresnel images could be used to obtain distribution of the domains, etc. This is one such example which is taken from the literature. This is on a magnetic data storage device, okay, where how on the tip the magnetic particles are distributed, and not only that, these are also magnetized. Okay. Some data is being stored. Because of that, when it is a slight defocus condition, when we get it, because of the Fresnel diffraction, we are able to see a contrast of this domain. Okay. Then another way in which a magnetic domain boundary can be get information about it is that, suppose we consider this is the sample, across this boundary, okay, the magnetic domains are oriented in two different directions, okay, because, and when that electron beam is coming like this, okay, these orientations can make the beam in one direction go like this and another direction shift the beam like this, and these beams can also interfere, okay, and this will give rise to an interference fringe contrast. This is the biprism, Fresnel biprism, okay, and with which also the domain boundary could be imaged. Okay. This is just an interference contrast. So, these are all the various ways in which we can get information about the magnetic domains. Okay. Now, what we will do it is that other techniques we have already covered. So, now we will talk about electron holography. I mentioned that electron holography is one of very important technique, okay, because using this technique we can get information about the phase as well as the amplitude, okay, of that sample. Okay. How exactly it is electron holography is done? There are many versions of it. It is called as an inline electron holography, off axis electron holography. Okay. There are many types are there. Okay. This is essentially a schematic diagram of an inline electron holography. So, what is holography essentially? This was discovered by Gerber, okay, way back in 50s. Essentially, if a coherent beam passes through a sample, okay, that is a beam, we split it into two. Okay. One part passes through that sample, okay, and the amplitude of the wave which comes out, there are some phase changes will be occurring in that sample, and if we mix with that reference wave, okay, when these two beams are coherent beams, they will give rise to a sort of an interference fringe contrast. Okay. This interference fringe contrast contains information about the phase as well as amplitude of that sample. Okay. If we use either that same beam or another beam, we allow it to pass through the image as well as mix it with the reference beam, we will be able to get information about that we will be able to form from the hologram the image of that sample. Okay. And that image is essentially formed because of the phase information which is available. The same thing can be done now if we have a hologram which is there, we can use computers to do all this job, get all the information can be obtained. Okay. So, what is essentially done is that this is a electron lens which focuses the sample, which focuses the electron beam right in front of that sample, and the beam is passing through, and some of the electrons are passing through the sample which is scattered from here, and this is the one which is assuming that is reference beam. These two interfere together, okay, and then gives rise to a contrast. Okay. This is the contrast which has information about the phase as well as the amplitude. Okay. So far we talked about essentially the holography which is inline holography. Offline holography is essentially which is very similar to the Fresnel biprism which we explained in one of the earlier classes. Here what is being done is that this is the specimen through which the part of the electron beam passes through, and this is the reference beam, okay, and all the beam in passes through. Here we have a Fresnel biprism is there which is splitting the so what is Fresnel biprism? Here what we do essentially, this is like a small glass coated with conducting material, and to which if we apply a voltage, this will be scattering the electrons in different directions, okay, and this is the direct beam which interferes with the beam which is scattered through the sample, and this will give a holographic image which it will be creating. Okay. This is one such holographic image which is obtained from a silicon is shown. Okay, 110 oriented silicon is being shown. But here if you look at it, there are two types of fringes which we can see. There is one fringe contrast which is larger spacing, and another is a fringe contrast which is a fine spacing. The fine spacing one corresponds to the conventional high resolution microscopy, and the larger one which appears, they have about 70 nanometer spacing. These are all the ones which can be used to get information about the phase as well as the amplitude distribution in the sample. That is, or in effect we can get the structure information about that sample from this hologram. Okay. Okay. Another important thing which you should understand here is that in this particular case the sample is not a magnetic material. Okay. It could be any sample. So, the information which we give it is how the interaction with the electrostatic potential in that sample, the beam interacts. Okay. That is mixed with a reference beam, and that is how we generate a hologram. Okay. If the sample is a magnetic material, then what is essentially going to happen, and this is a particular case where a permalloy sample is supported on a silicon nitride substrate. Okay. Here again we can see that the holographic image, there is some bending of these bands are there. These fringe shifts are taking place because of the magnetic nature of the material or how the magnetic domains are distributed. What is important which one should realize is that in the Lorentz microscopy we used to get information about the distribution of magnetic domains. In that case I mentioned that we can't get any quantitative information about the magnetic field, whereas in this particular case we can get information about how the domains are distributed, not only about how the domains are distributed in that sample, we can also quantitatively get information about the magnetic induction in that sample. That is the great advantage of using. So, essentially we can say that the magnetic potential variation in that sample, that information could be obtained using electron holography. This is essentially taken from the literature, essentially a holographic image of a magnetic cobalt particle. Okay. This is a reconstructed image of that particle which we see, this is how it looks like. Okay. In a conventional microscope if we look at it, we do not get much information, but if you use a holographic electron holography technique which is attached to a microscope, then we can get information about how the magnetic field lines are distributed in and around that sample. Okay. And see the interferometry image which we get it of the sample, and this is for a single particle, and here essentially is in a magnetic medium. Okay. How the magnetic field, the domains are oriented, okay. How the magnetic valves are oriented, all this information which we can get it. Similarly, suppose we take a superconducting magnet, thin film superconducting magnets, we wanted to know how the field lines penetrate through that sample as we change the temperature. All these experiments we could get, and information about how much of the magnetic induction is getting passing through the sample, penetrating the superconducting sample. This information could be obtained using this technique. That is, we can directly image and quantify it also. This is one of the greatest advantages, okay, of using electron holography. But the microscope, to use this technique, the first thing which we require is that the wavelength of the radiation, okay, should be some value, that is for the microscope. But what is essentially important is that the energy spread should be as little as possible, then only we can get reliable interference pattern. That means that field emission gun with, okay, filter, if we use it, we can reduce that effect of the chromatic aberration in that microscope. Path difference of the electron is changed into a phase changes, or the phase change is converted into the path change. Okay. In all these cases the beam has to be as monochromatic as possible for all this experimental work to be done. So, to ensure the monochromaticity, okay, that we have to make the line width as small as possible. Okay. The energy spread of the beam can be reduced only if we use field emission gun, and that too if we use a filter, the energy spread, as I mentioned earlier in the last class, it could be made as small as about some 0.2 electron volt. Okay. This is another example where it is a hologram of a PMOS transistor which has been taken. Okay. This is the holographic image. Okay. Then how do we get an information from the hologram? Because we use a reference beam, though this hologram has been generated using an electron microscope. Okay. To reconstruct the sample information, we can use any beam. It could be a laser beam which we could use it, or we can use a computer to use some mathematical processing to get these images. Okay. So, here if you see it, this is what it is a P plus region, this is the gate. Okay. And this image, as I mentioned, that we can get information about the amplitude. Okay. That is that amplitude information about what is the mass, which is elements which are remaining, all those information which we get, the amplitude information of the phase, and this is the phase information also of the phases we could get. Okay. This darker region shows that the phase is quite different compared to that of this N region. Okay. And this also shows that there are some variations in the phase. Okay. And this periodic variations of the phase is taking place. All these informations we can get in material. That is not only for magnetic material, the magnetic potentials, electrostatic effects also bring about changes in the holographic images. That gives information about the electrostatic potentials. Okay. That information also could be obtained using electron hologram. Though in principle when we talk about it, this looks like a very simple technique, but extracting information requires a lot of deep understanding of the physics behind these processes. Okay. Lot of detailed software have been written. Okay. One should understand what all phenomena which occur to get that information. But what is the advantage essentially is that from one micrograph which has been generated, one hologram, we can get complete information about the phase and that amplitude. Whereas in a high resolution microscopy, as I mentioned, to get correct structure information, we may have to make the contrast matching for at least a few images which are taken for different defocus conditions. Okay. Now, I will talk about the other technique, the time resolved or dynamic electron microscopy. Okay. The problem in a conventional electron microscope is that since the electron beam is falling onto the sample surface, if it is a metallic sample, okay, and if the beam current is relatively small, okay, the beam passes through it and without generating much damage within that sample. Whereas in the case of biological samples, when that electron beam passes through that sample, if it is focused, then they can damage the sample during observation itself. The time which it takes for this damage to take place could be so small that before we complete the examination of that sample, the sample might have been completely damaged. So, this is a very serious problem in many microscopes. Okay. So, how this could be studied? Okay, that is that which was thought is that if we make the electron beam, pulse the electron beam if we use it, okay, we make the beam pulse, very small pulses are being made. Okay, these pulses are of some few nanosecond separation between them and femtosecond duration. Okay. These pulses are generated using an LAB6 filament, but in a normal microscope LAB6 is heated and electrons are generated. Instead, in this one what is being done is a laser pulse is allowed to fall on the LAB6, okay, some ultraviolet laser radiation, and that generates photoelectrons. Okay. Since these photoelectrons are coming out, okay, these photoelectrons are narrow spread in energy, okay, and short pulses they come out of that then they are accelerated to high energy and they are allowed to pass through the sample. So, all the information about the interaction of the beam with the sample for each of the pulse is collected. So, this way we can get information. Suppose some chemical process is going on, okay. We wanted to find out how actually the one phase is forming by an interaction, that is in some gas cell we can do it, some gas reaction. So, that is how the chemical reaction takes place to form a phase. All this information could be studied in situ, that is why this is called as a time resolved electron microscopy. Okay. And in beam sensitive material where this here we can control, so that since short pulses we are using it, we can get information about the sample from each of the pulses. Okay. And in all these cases what has to be done is that we do not photograph that image, essentially that the electron beam as it passes through the sample, it is collected, okay, using a slow scan CCD camera, and then this has to be that digital data has to be processed to get information about how the changes are occurring within this sample. Okay. So, it is a very important technique with which, since that femtosecond nanosecond duration pulses with femtosecond pulse width which we are using it. So, this is of the order of dimensions where the atom movement takes place within that sample, because of which in many areas like catalysis or in chemical reactions, how atoms move from one side to another, how that interaction takes place, all this information could be studied. This is a very powerful technique, and this technique has started coming up. Okay. These are all the trends which I wanted to talk about. But what is essentially important is that it's all has come out because people have seen some limitations. When you start using the microscope, you see what you can get from the sample. One has to use an imagination to decide, okay, how to conduct an experiment, so that some changes may have to be made to a microscope, or some small special holders or setup has to be made, so that the type of experiment which you wanted to get to get the information which you are looking for, that could be performed. So, the whole microscopy field, for that matter, like any other field, is an evolving field where lot of new ideas are being used to develop new types of microscopes. Okay. To get best use of that all this equipment, one has to apply one's own mind. So, essentially the equipment can give some raw data. How to analyze and interpret is how we look at the data which we have got, okay, and how determined we are to get the best out of it. Okay. That is the way we have to get that information. So, essentially in this lecture I have talked about the various techniques which are available. That is the new modern trends which I have talked about it. Okay. Maybe in future you find that many more new techniques, new powerful techniques will come up in the electron microscope. Okay. I will stop here. Thank you.